The solubility of carboxylic acids is quite variable, and what it really depends upon is how big the carboxylic acid is. So it really depends on which group dominates. If we have a very, very long hydrocarbon tail with our carboxylic group right here, then this nonpolar group may dominate, and the characteristics may be more nonpolar than polar, so it is not likely going to be as soluble. However, if we have a short, itty bitty teeny weeny R group, they tend to be more soluble or more polar. So if we break it down, it ends up that if we have between 1 and 4 carbons, they are considered water soluble. Between 5 and 7 carbons are slightly water soluble. And if you have more than 8 carbons, they're considered insoluble. So again, the longer that hydrocarbon chain, the more nonpolar the characteristics are of any substance, and the more that they're going to resemble the nonpolar hydrocarbons. So carboxylic acids have relatively high boiling points, and it has to do with the intermolecular attractions of hydrogen bonding. And they have the highest boiling point of all of the organic compounds we have studied. So if we look at this, we can have a hydrogen bonding occurring between the hydroxyl group on one carboxylic acid group and this carbonyl group on another. So you see that dot, 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 dot. Oh, my dots are very, very little. Dot, 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 representing that hydrogen bond, and then you have that again there. Now, remember, the more hydrogen bonding you have in any substance, the stronger the intermolecular forces, and that results in higher boiling points. It's really hard. It takes a lot of energy to get those molecules apart. And this picture is just showing a blown up version of what's on that last slide. So this is just some facts about carboxylic acids. Acetic acid is present in vinegar, so most of the vinegars that you get over the counter are a 5% solution of acetic acid. When we have pure acetic acid, it's called glacial acetic acid because of its freezing point being at 17 degrees Celsius. When you use glacial acetic acid, it has an extremely strong vinegary smell, as you might be able to imagine. Oxalic acid, which is that dicarboxylic acid that we talked about before, is present in its salt form, which we'll talk a little bit more about what a salt form is for carboxylic acids later, in some leafy plants, and it's also used as an anticoagulant. And we'll come back to this a little bit later too. It can be very poisonous at high levels, and it can be found in rhubarb. Alpha hydroxy acids are often used in skincare products. They are known to more quickly regenerate your skin cells, which means that as you're washing your skin cells slough off and they get regenerated faster, and leads to a more youthful appearance. So I'll remind you again that alpha refers to the position of the hydroxyl group on the alpha carbon. So glycolic acid here is 2-hydroxy ethanoic acid. So ethanoic acid contains 2 carbons, and if it's a 2-hydroxy, that hydroxy group is going to be right there. And this is called an alpha hydroxy group, or an alpha hydroxy acid, because this OH group is on that number 2 carbon, which is the alpha carbon. Lactic acid is 2-hydroxypropanoic acid. So lactic acid is found in our muscles when our muscles are being starved of oxygen. So it is a byproduct of excessive muscle use, and also a hydroxy acid. So alpha hydroxy acids, the glycolic acid and the lactic acid, I believe, are body hydroxy acids, but alpha hydroxy acids are often also used in beauty products. Salicylic acid is can be found in willow bark, and it is known to reduce fever, reduce inflammation, and be a pain reliever. And salicylic acid is 2-hydroxybenzoic acid, so this is a benzene ring. Ooh, that is wonderful. And we have our carboxylate group right here, and the number 2 carbon is right there. So salicylic acid is the active ingredient in aspirins. It's what we use to make aspirin. And also it is used in acne medicines to help kill bacteria in acne medicines. So the next thing I want to talk about are the acid-base properties of a carboxylic acid. But before I do that, I want to just review the acidic properties of an acid, as you may have learned in general chemistry. So I will take hydrochloric acid here. So let's say I have HCl, and I combine it with water. So when we're talking about the acidic properties of a substance, we're talking about what's happening when we combine it with water. And the same can be said for the basic properties of a substance, which will become important when we're talking about amines. So if we take hydrochloric acid, HCl, and put it in water, what happens is this hydrogen ion gets ripped off the molecule, and it's going to get stuck on that. So the hydrogen ion is donated to the water. All right. Now what that results in is this right here, which is called hydronium. So an acid, according to the Bronsted-Lowry definition, is called a proton donor, and a base is the water in this case is acting as a base, which is called a proton acceptor. I can't write very fast with this. I'm sorry. So what's this proton business all about? Proton donor, proton acceptor? Well, in chemistry, another name for a hydrogen ion, I'll just write it down here. This is H plus. A hydrogen ion is known as a proton. And the reason that is because if you take the nucleus of the most common hydrogen atom, it contains 0 neutrons and 1 proton. Now, if it's an ion, that hydrogen had 1 electron to begin with. Now, if it's an ion, it means that this electron has been ripped away. It has ionized it, has lost it, and it leaves behind a proton. So a hydrogen ion is also known as a proton. All right, so a donor, proton donor is an acid. This acid is donating it to this. Now, when you notice acid-base properties, one of the ways you can recognize an acid is the fact that we're producing this hydronium here. And what it leaves behind is chloride ion. So an excess of hydronium ion in solution leads to acidic properties. And acidic properties include a pH of less than 7. It will turn blue litmus paper red. My pen is going slower than molasses in January. The acids tend to have a sour taste, so these are just some properties of acids. Now, I am going to go back now and look at this. So here is acetic acid. And acetic acid is also known as ethanoic acid. What happens is it gets cleaved or cut right here, and this hydrogen ion is lost, and it gets donated to the water, producing hydronium ion. And then this right here is called an acetate ion. And in general, when a carboxylic acid loses this hydrogen proton, this hydrogen proton, this proton, hydrogen ion, the general name for a product is called the carboxylate ion. And a carboxylate ion has a negative charge, so this whole massive thing has a negative charge, and it can often bond with substances like sodium or potassium and produce what's called a carboxylate salt. So if acetic acid is added to a sodium compound, one of the things that can happen is the acetic acid is, these reactions are often occurring in water. So the acetic acid loses some of its hydrogen ions to produce hydronium, which gives it the acidic properties, and the carboxylate ions, and you can get sodium carboxylate. In this case, it would be called sodium acetate. Since this is actually called ethanoic acid, the technical name of this would be called ethanoate. So a carboxylate ion has the name of ethanoate. So that is going to conclude this video. I have lost my drawings already, so I'm going to end this video with the acid-base properties. I have a couple other videos showing acid-base properties of carboxylic acids that can help support this concept, and I will give you access to those as well.